Now then, back to the session. Our first speaker will be John Evans on radar measurements on Plasmasphere-Ionosphere Coupling.
What I would like to try to do is briefly summarize for you the contributions that incoherent scatter can make to studying plasma exchange between the ionosphere and the magnetosphere and exchange of heat between those two regions. The stations that are constructed and unavailable, that are available to make measurements are listed here. Unfortunately, very few of the existing incoherent scatter facilities are sensitive enough to make the kinds of measurements I'll be describing. And I'll largely limit my remarks to observations made from Arecibo, Puerto Rico, to an L value of 1.4, in other words, well inside the plasmasphere, and observations made from Millstone to an L value of 3.2, which is therefore sometimes inside and sometimes outside the plasmasphere. Now, let me remind you that scattering by the incoherent scatter process comes when the radar signals are reflected from density fluctuations in the plasma, which are produced by the presence of the ions. And therefore, the actual nature of the Doppler broadening of the scattered signal depends on the ion mass. This is shown in the next slide. For oxygen ions, the Doppler broadening will be a certain amount for a given ion temperature. If you lower the ion mass, say to helium, it'll be twice as wide. And if you reduce it to hydrogen, H plus ions, it'll be twice as wide again. The shape also depends on the electron to ion temperature ratio. So basically, one of the first things you can do with an incoherent scatter radar is locate the plasma pores. In practice, there's a large region where you have a mixture of ions, and you may have both H plus, O plus, and helium plus all mixed in. And then the spectrum shapes get very complicated and also depend on electron to ion temperature ratio, and it gets a mess to sort out. In practice, what people did in the earliest days, such as the Ticker marker, was to assume that there was no helium plus present. Then you could interpret the spectra and derive a transition altitude and profiles of the oxygen and proton densities. This kind of work has been done at Arecibo. These are some results from a paper by Ho and Moorcroft. This is the concentration in percentage of the H plus ions for different altitudes as a function of time over Arecibo. Using this data and simple chemical equilibrium theory, one can derive the actual neutral abundance of the hydrogen, assuming an oxygen abundance from, say, some model, in this case the USU 65. Now, this neutral abundance is an important parameter because it governs the escape flux, the maximum escape flux that Peter Banks described. You see a diurnal variation here of the order of 2 to 1. We don't yet really know how the hydrogen is distributed around the globe very well, and especially at high latitudes where we have a great deal of heating going on, there may be regions where the neutral hydrogen is quite depleted and our ability to recharge field tubes is quite low because there's very little neutral hydrogen available to do it with. In this work, Ho and Moorcroft actually solved a continuity equation to derive fluxes that were present and came up with these results. They had fluxes of the order of 10 to the 9th. However, I think there's something wrong with this, that the results are too high, in part I think because their hydrogen values are too high because they took the wrong oxygen values from the Kia 65, had the wrong oxygen in it, and in part because they neglected various terms in their solution, such as any flux produced by the growth or decay of the layer, which they couldn't measure. We can, however, measure directly the flux. I'm sorry, I'm going too fast. These are the kind of data coming out of Arecibo now, where they have a new improved feed and data processing equipment. In the daytime, they're still obliged to assume that helium is absent and solve for O plus, H plus in the electron to ion temperature ratio. See a transition altitude at this particular time of 1,400 kilometers. At night, however, they can solve for all three parameters because they can now assume that the electrons and ions are at the same temperature. And so you see abundances of all three constituents. This is some recent work by Hagen and Su. In addition, they're able to measure the velocity of the plasma. This is done by observing as the whole spectrum is Doppler shifted if the plasma is moving. If it's all coming towards you, then there's an appropriate Doppler shift to higher frequency values. And using this approach, they have the vertical velocity of the plasma at various altitudes. You see the plasma is moving up during the daytime, largely, and at sunset comes cascading down, and then persists to have negative velocities, or downward velocities, throughout most of the night. And from this kind of data, one can unambiguously get the flux, and Hagen and Su observe fluxes of the order of about 2 times 10 to the 8th, say downwards in the downwards at night and upwards in the daytime. And these are lower than the Moorcroft values, but I think are much more reasonable. As one proceeds to higher latitudes, to Millstone, we've never been able to detect the transition altitude. And this seems to be because at Millstone, you're just on the inside of on the outside rather of the light ion trough. You're somewhere on the edge of the light ion trough. Transition altitude lies perhaps at 1,500 or 2,000 kilometers, and our radar is not sensitive enough to see it. However, we can see oxygen fluxes going on in the upper F region. If we make the same kind of vertical velocity measurements at, say, 600 kilometers, we're observing fluxes now of oxygen. We see an upward flux at dawn, a downward flux at sunset, oscillations produced by TIDs that run through. But we can try and pick a period of day when steady state seems to be established by looking, for example, at the electron density profiles that go along and noting that, say, for some period between, say, perhaps noon and 4 o'clock, the electron density contours are running horizontal, and that the electron temperature contours are running horizontal. There's no change in the plasma pressure going on. Therefore, that vertical velocity we see of the O plus flux, of the O plus must mean a flux that's not due to the growth or decay of the layer. And using that approach, Shunk and Walker have taken this oxygen data and used a theory to predict what the fluxes should be. Below about 500 kilometers, any O plus ion that's created has to move downward and is lost below the peak of the F layer around, say, 220 kilometers. O plus that's created above this level, however, diffuses upwards into the protonosphere, reaches a peak flux of about 10 to the 8th. The flux then drops off as more and more of it is carried by protons that we don't see in our measurement. And these are the points are the measurements. The theory is the solid line of Shunk and Walker. And they also are able to match electron density profile when they include such things as thermal diffusion and neutral winds. They actually derived a neutral wind speed of about 200 meters a second, which I think is a bit high. Their flux, however, was quite reasonable. It was about 1.2 times 10 to the 8th. Here is their computed hydrogen density as a function of altitude, and this is the flux they estimate to be occurring. So one can derive also fluxes from the Millstone data, at least for the steady state conditions. It's a little bit more difficult when the layer is decaying or growing. Now, turning to the transition or the transfer of energy between the ionosphere and the magnetosphere, one has a very simple way from Thomson scatter observations to measure heat fluxes. What one gets in a typical measurement is an electron density profile as a function of altitude and electron and ion temperatures. And from the electron temperature gradient, and in our case we use the Spitzer formula, which seems at least from Brace's measurements to be acceptable below 1,000 kilometers, compute what heat flux must be carried by these electrons in order to sustain this temperature gradient. The thing we've tended to do at Millstone a great deal is average a lot of the data with time. Typically, we average over 6 hours of nighttime, 3 hours before and after midnight, and 5 hours of daytime data between, say, 10 in the morning and 3 in the afternoon. And we have a whole raft of these average curves from which we compute the fluxes. And when you do this, you generally find, of course, the flux is much greater by day than by night. But on rare occasions, we see the average nighttime temperatures are indeed higher than the average daytime temperatures. And this, of course, is a little bit surprising. The typical fluxes we see plotted, say, over one particular year, run around in the daytime some average value, which is about perhaps 5 times 10 to the 9th. In winter, the flux is about half this during the winter nights, we believe, because in our case the conjugate point remains sunlit throughout the winter night, but drops in summer when both ends of the field tube are dark to some value of the order of 2 times 10 to the 8th, which is the vestigial amount of heat that the field tube can sort of sustain throughout the whole night. This is the winter case, and one sees these much lower values, except when a magnetic storm is in progress, and then you can get a very large value, as large as the daytime case. This particular high flux occurred on a night when these are the electron density contours logged to the base 10. When the electron densities are extremely low, we have just over 10 to the 4th electrons around the peak of the F layer over Millstone. Millstone is presumably now lying in the trough near the equatorward edge of the trough. And this confirms, I think, things that Larry Brace and others have said, namely when you get close to the trough or just over into it, you experience these very low densities associated with very high temperatures. You see these the temperatures started to rise here and persisted to about here. Large influx of heat for a period of the night associated with very low densities. This is a feature that we consistently see. We can see it in the daytime, though less clearly, because in the daytime electron densities tend to be higher and tend to diminish the temperature rise that would then occur for that same heat influx. If one takes a long-term average, one sees that the fluxes tend to rise with sunspot flux. These heat fluxes tend to rise with sunspot fluxes, is something you might expect. However, we notice a consistent difference. If you average over 6 months of summer and 6 months of winter, there's more heat comes down from the magnetosphere in winter, at least at Millstone, than in summer. And this I don't have a ready explanation for, but I noticed that Chung Park also finds a difference in the number of electrons on the field tube between summer and winter, there being more in winter, suggesting that the photoelectrons that go up into the ionosphere are more likely to lose their heat in trying to get over to the other side in winter than in summer, and therefore they lose it on the field line, whereas many get through to the other side in summer. My last topic is measurement of the photoelectron fluxes. The component of the spectrum that we've been discussing is this component that's reflected at the radar frequency or very close to it. There are, in addition, however, fluctuations in the plasma which involve the electrons interacting with themselves, which also give rise to scattering. And these give rise to two lines displaced from the radar frequency by an amount that's approximately equal to the plasma frequency. In other words, if you're reflecting from a level where the plasma frequency is 4 megacycles, 4 megacycles away from the radar frequency on either side will be these two weak reflections. Now, these are enhanced in the daytime by the presence of fast photoelectrons. These excite the plasma waves that give rise to this scattering. And if you'll bear with me, the phase velocity that one gets for these waves is simply that that Doppler offset, Fr, is related to the phase velocity of the wave by F sub r times your wavelength upon 2. And the energy, therefore, of the photoelectron that's exciting this wave is simply E½ m electron v phase squared. So as you change the frequency of the offset, or the height at which you're looking, you're seeing photoelectrons with different energy. So in a sense, you have a spectrum analyzer, And if you take measurements above the peak of the layer and assume that there's constant flux going out, by looking at different levels where the plasma frequency is different, you can select out different photoelectron energies and therefore get something about the velocity distribution of the photoelectrons. It's just a one-dimensional velocity distribution. And from this, it's very difficult, in fact, to determine a three-dimensional velocity distribution. What in practice has been done, usually, is to work the other way. I perhaps should say a little bit more. One can't explore over a great range of photoelectron energies. Low energies, one tends to run into the thermal background, and so one only can see down to some low energy set by the presence of the ambient electrons, and at some high energy, there's a cutoff due to collisions. And the kind of thing one sees is a temperature of this plasma line of some energy range, which might be measured either approaching the radar or going away from the radar like this. And the simplest thing to do is then try and make a theory which reproduces the radar observations. And this has been done by a number of groups, principally Ralph Cicerone. This is a match between measured and calculated values for when only one end of the field line was lit. This was a case when millstone was in the dark, but photoelectrons were spiraling over from its conjugate point and producing plasma lines at millstone. And the agreement is too good to be believed, but this is the kind of approach that has been made to get photoelectron fluxes, and I think Ralph Cicerone will say a little bit more on that when he talks. Thank you.
I'm so well behaved, we'll have to squander at least two questions on him. Dr. Robert?
It's a question about the H plus O plus transition altitude. I think you said that you don't ever observe that at Millstone Hill.
No, we never have. We've looked
Yes.
for it, but it seems to be higher than we can see.
Now, presumably during the daytime it's because it's high, but surely at night time, would it not because of the low concentrations rather than because it's high?
Well, you're fighting two things. Your ability to look high up at night goes down simply as the electron density goes
So in fact,
down. Your sensitivity.
The transition altitude can't come down and you wouldn't see it.
The point to which you can see is moving up by day and night, and it's probably staying below the transition altitude at all times, is what seems to be happening.
You made a statement that it seems that photoelectrons lose their energy more efficiently in the protonosphere in winter than in summer. Now, it sounds almost like hemispheric chauvinism, but it should be, because when it's summer here, it's winter at the other side, so maybe you can explain that a little bit.
I have no ready explanation. I asked Chung Park to explain why he sees more electrons in the field tube in winter than summer.
What's that? What did you quote him as saying?
If he measures the total tube content, he has at least, maybe you can confirm this, Chang, you have at least one set of data that shows, I think it was 64, a total field tube content which was higher in winter than summer.
December versus June.
Yeah, northern winter versus...
We are really measuring the total content from one hemisphere to the other. So there is really no seasonal difference. The variation is that the total content from southern to northern hemisphere is higher in December compared to June. So it will be northern hemisphere winter.
Yes, it's
The
of
northern
sense to
hemisphere winter is
explain this
higher.
anomaly, but I don't have an explanation for why it should be so.
I think we better move on. Thank you, John.